So Anjali from my group is going to present some work on dataset design. Anjali was an undergrad at Berkeley, and she's now a rising third-year graduate student working on our ML projects. And she'll tell you about a story that we recently published and that we're continuing to work on.
Hello, thank you for that introduction. I'm excited to share some of our work on designing target-specific datasets for predicting regioselectivity on complex substrates. As Sarah mentioned, my name is Anjali, and I'm a student in the Reisman group at Caltech. And in the Reisman group, we're interested in the synthesis of complex molecules. And one step that we use to do this is a CH activation. However, what we found is when implementing these steps at a late stage, it can be quite risky, as in the case of the synthesis of savoleucolin B. This is because it is difficult to know beforehand what the regioselectivity of one of these steps might be on a complex substrates, leading to complex mixtures of radioisomers on late-stage substrates that are different. To address this, chemists might turn to a model for regioselectivity. If these models work well on their target, they can then get a better sense of whether this proposed step will work in their synthesis. And there are several models for this. They primarily focus on CSP2H regioselectivity prediction, and they seem to perform reasonably well. However, the question for a synthetic chemist who wants to use this model is, how do they know that the model will perform well on their specific target of interest? What this question boils down to is whether that target is in the model's domain of applicability. And one way you could ensure that this is true is to build a really big foundational model with a large, diverse data set that has a domain of applicability that spans the entirety of all chemical space. However, in synthetic chemistry, the amount of data required to do this is often unavailable, and developing a model that can perform well on this broad space can be challenging, as reactivity space is not smooth due to subtle changes in mechanism and activity cliffs. So we proposed a contrasting approach where instead, since in a synthetic planning context, you know which substrate you're proposing, you could design a small training set that is guaranteed to represent that target molecule. To test out this concept, we extracted a data set of dioxarine oxidations from journal articles, and we set up a split where we had small molecules that we aimed to represent accessible compounds that a chemist might not mind running the reaction on to develop a training set for their ultimate target. We also set out a set of complex molecules, which were meant to represent those complicated synthetic intermediates that a chemist would be interested in predicting on. With this data set in hand, we developed some modeling using a random forest model, and then we moved on to this question of how do you make a training molecule that will predict well on a target. To start with, we thought about chemical similarity. We split this up into scaffold or substructural similarity between the candidate training molecule and the target. About CH site similarity, so the similarity in descriptors between a CH site on a candidate molecule and the target. We also took into account some active learning considerations using the model's predicted reactivity and uncertainty to focus candidate selection towards reactive and uncertain areas on a target molecule. With these various factors, we designed a suite of acquisition functions that we would use to score the candidate molecules and then suggest the next training data point for the chemist to perform. To evaluate this workflow, we simulated it on our literature data set, where you start with one of our complex target molecules, you set out a single molecule as the modeling start point, and then you use an acquisition function to select each subsequent molecule from that literature set of accessible compounds, evaluating performance at each point. And what we find is that we see significant improvements in the dataset size necessary to reach stable accuracy with these acquisition functions over random selection. This plot on the right corresponds to the steroid you see on the left, and if we take a look at these shows, that represents a stable period of accuracy where over 10 additional data points, you see performance over 90% on extracting that the most reactive carbon is indeed the most reactive predicted. And we see that with random selection, you need over 80 data points to reach this period of stable accuracy, but with our best acquisition functions, you can reach that point in under 20. And this is true beyond just that steroid I showed on the previous slide. On a median across our 50 complex target molecules, we see an improvement of 40 data points over random selection with our active learning acquisition function. We also see this benefit on 5 of our stockroom and archive compounds from past projects that were meant to be complex targets that we tested experimentally in-house. We also find that this workflow is not limited just to dioxazine oxidations. For CH borrelations as well, we see this improvement in data set size needed to achieve good accuracy. Moreover, what we find is for 12 of our complex targets, using an acquisition function, we a stable accuracy where you would never achieve that accuracy with the full data set that we had available. So our overall takeaway from this work, which other works in this area have found, is that more data isn't always better. Using a small data set that covers only the relevant region of chemical space that maybe is easier to model together can outperform a larger data set that has a more challenging modeling task across a broader region of chemical space. And with that, I'd like to thank our group. So I'd like to thank Sarah for being a great advisor, my project partners Joel Schleinitz, Alba Carretero Cerdan, and Anat Milo and Jonathan Harnick at Ben Gurion, as well as our undergrads that we've worked with, Gina Lee, Mitesh Pandey, and Carolyn Wan. I'd like to thank you for your attention and these agencies for funding, and I'm happy to take any questions.